Imagine you have a world with a charge distribution of rho 1, which creates an electric potential of phi 1. Then imagine another world, a completely other world, which has a charge distribution of rho 2, which creates an electric potential of phi 2. If phi 1 and phi 2 are 0 at the infinities, at really long distances, we don't want bad things to happen. What I'm going to prove is that the integral of rho 1 times phi 2 dv is same as the integral of rho 2 phi 1 dv over all of the space. And this guy is all the space. Yeah, I know it sounds a little bit insane, but it's true. So at first I'm going to prove that for any scalar field, scalar fields like phi 1 and phi 2, the divergence of phi 1 times gradient of phi 2 is the dot product of gradient of phi 1 and gradient of phi 2 plus phi 1 times Laplacian of phi 2. So this guy over here, I think it's easy to show that, it's obvious that it's the derivative with respect to x of phi 1 times derivative of phi 2 with respect to x plus derivative with respect to y of phi 1 times derivative of phi 2 with respect to y, and same thing for the z-axis. Yeah, if I use the product rule for differentiation, I'll write this guy as the differential of phi 1 with respect to x times differential of phi 2 with respect to x plus phi 1 times the second derivative of phi 2 with respect to x plus the same thing for the y-axis and the z-axis. Yeah, I think now it's obvious that these terms are this guy, and these terms are phi 1 times Laplacian of phi 2. So yeah, now we know that this guy is true. So now I can write gradient of phi 1, the dot product of gradient of phi 1 and phi 2 as the divergence of phi 1 times gradient phi 2 minus phi 1 times Laplacian of phi 2. Yeah, if I swap the places of phi 1 and phi 2, this guy over here doesn't change, but these two guys change. These guys change to divergence of phi 2 times gradient of phi 1 minus phi 2 times Laplacian of phi 1. Yeah. So if now we've got these beautiful identity, if I integrate both sides of this equation over a random volume, I'm going to call it V, what we would have is that the integral of divergence of phi 1 times gradient of phi 2 minus phi 1 Laplacian of phi 2, yeah, dv is same as the integral of divergence of phi 2 times gradient of phi 1 minus phi 2 Laplacian of phi 1 dv. Yeah, so let me clean up a little bit. Okay, now I can use the divergence theorem for these terms and change these volume integrals into two closed surface integrals. I'm going to call it surface S, which S is the bound of this volume, is the bounds of this volume V here. Yeah, I can write this as the integral over S of phi 1 times gradient of phi 2 times dA, dot product. ds, I think, is better. Yeah. Minus integral over V of phi 1 Laplacian of phi 2 dV. This guy is same as the integral over S of phi 2 gradient of phi 1 ds minus the integral over V of phi 2 times Laplacian of phi 1 dV. Yeah. So if you remember what we said at first, if this volume V here is all of the space, this surface would be at the infinity. This bounds would be at infinity. And we know that at infinity, phi 2 and phi 1 are 0. So if V is all of space, what we would have is that this term would be 0 and this term would be 0. So now what we have is that the integral over V, which I'm going to over all of space, of phi 1 times Laplacian of phi 2 dV is equal to the integral over all of space of phi 2 Laplacian of phi 1 dV. Now, as we know, Laplacian of phi 2 is rho 2, is minus rho 2 over epsilon 0, and Laplacian of phi 1 is minus rho 1 over epsilon 0. So this guy over here is minus rho 2 over epsilon 0, and this guy over here is minus rho 1 over epsilon 0. Now these epsilon 0s cancel out, also these negative signs, and what we would have is that integral over all space of rho 1 phi 1 dV is same as integral over all space of rho 2 rho 1 phi 2 rho 2 phi 1 dV. And that's it. Yeah. It's just insane. It's crazy. This theorem is just, it's not only beautiful, it's just so freaking powerful. In one of my next videos, I'm going to solve a problem with this theorem to show you how powerful this theorem is. It's just insane. And yeah, that's it. I hope you guys enjoyed it, and see you later.